We're going to take a look at a different type of example, not one that relates to volumes, but one that relates to another aspect of something that could happen here with related rates. This problem says an aircraft is flying at 500 miles per hour with an elevation of 10,000 feet on a straight line path that will take it directly over an anti-aircraft gun. How fast must the gun be able to turn to accurately track the aircraft when the plane is 1 mile away, 0.2 miles away, and directly overhead? This is a very different type of problem because we're talking about the gun being able to turn. So let's draw this out in a rough sketch so that we can kind of figure out what's going on. So we have a plane flying over. I'm going to draw a plane. Well, I'm not going to draw a plane. I'm just going to draw a little circle that represents a plane. So we have a plane, and it's flying in a certain direction. And then there's an anti-aircraft gun on the ground. So there's a gun here. All right, and I'm just going to draw a circle for that. Now, the elevation of the plane, let me draw elevation. We'll draw that in green. The elevation of the plane above the ground is 10,000 feet. And it's going in this direction. Now, when we say it is 1 mile away, they're talking about this distance, 1 mile from being directly overhead. So it's going to be flying this way. And as it's flying, the angle that this gun is pointing is going to have to turn. So if as it flies from here to here, notice that the gun has to turn in that direction. So as it flies from spot A to spot B, the gun has to turn this much. So what is the rate at which that gun has to turn? This one is complicated in a couple of different ways. One way is the fact that the elevation is in feet, whereas the ground distance is labeled in miles. It also is interesting that we're talking about an angle here. Let's call that angle theta, just for the purposes of what we're doing. So we have a theta angle and versus a distance, where in the last couple of problems, we were talking about the idea of centimeters and square centimeters. So they're related in a little bit more concrete way. So the first thing we're going to do is or convert miles into feet. We want everything to be in the same units. And if you don't know this, 1 mile is 5,280 feet. And I don't expect you to have that memorized. So 5,280 feet is the distance of 1 mile. As far as this angle goes, what I'm going to do is I'm going to look at that change in angle. Instead of looking at that angle, I'm going to look at this angle here. All right. So how fast is this angle changing? And so this is going to be eliminated. How fast is this angle increasing, this gray one? Hopefully that makes sense. How fast is this gray angle increasing? And in order to get a formula that relates this gray angle to the elevation of the plane and to the distance across, we need to go back to trig. And remember that the tangent of an angle is the opposite side divided by the adjacent side. In SOHCAHTOA, TOA, tangent is equal to opposite over adjacent. So tangent of the angle is opposite over adjacent. Tangent of theta. The opposite, if you remember, was the height of the plane. And I believe the plane was at 10,000 feet, if I'm right. And that's going to be constant. It's going to fly at a constant height throughout this whole process. The adjacent length, well, that's going to be variable. So we're going to call that some variable x. And we come up with this equation that relates the angle of the gun to the distance the plane is away. Now we can take a derivative. Derivative of tangent is secant squared. So we take secant squared theta, but then we have to multiply times the derivative of the inside function. And then we take a derivative of the right-hand side, derivative of 10,000 over x. Well, think of that as 10,000 times x to the minus 1. You get negative 10,000 divided by x squared dx dt. Now this looks a little bit messy, but we can fill some things out depending on where we are at. So let's assume the plane is 1 mile away. Remember, 1 mile is 5,280 feet. Okay. The other thing that's a little bit tricky is, if you recall from the initial problem, it says the plane has a speed of 500 miles per hour. Now I am going to change that to feet. 500 miles per hour. Since there are 5,280 feet in a mile, that's 264,000. In other words, 2,640,000 feet per hour. So I'm just multiplying there. And if you wanted to change that per second, that's okay too. Per hour, well, there are 60 minutes in an hour and did I say 60? Yeah, 60 minutes in an hour, 60 seconds in a minute. So there are 3,600 seconds per hour. And that means the plane speed 264,000 can be divided by 3,600, and you get 733 1/3. or 2,200 over 3 feet per second. That's how fast the plane is going. Hopefully that makes sense. I divided this number by 3,600 because there are 3,600 seconds in an hour. So this plane speed I'm going to think of as 2,200 divided by 3 feet per second. So I like thinking about rotating in terms of per second. How many degrees or how many radians per second do we rotate? All right, so when we're 1 mile away, that's 5,280 feet away. Remember, that was our x. That was our adjacent side. We can plug that in for our x in this equation. The rate we said was 2,200 over 3. So we plug 2,200 over 3 into that equation for our rate that the plane is flying. That's the change in x with respect to t. And then the only other thing I need to do is find the theta. Well, the one way I can find the theta is go back up here. If we're 1 mile away, then tangent of theta is equal to 10,000 over 5,280. That's 1 mile. So theta is whatever we get out by taking the inverse tangent of 10,000 divided by 5,280. My calculator is going to be set in radians. When I do that, when I type that into my calculator, I end up with 1.085 radians. All right. So the theta that we're going to plug in is 1.085 radians. Now that I have everything except for the d theta dt, I can go ahead and solve for d theta dt. Oh, I just noticed something, and I apologize for this, but when I drew my grid out, because the plane was moving towards the left, this speed should actually be a negative. Just realize that when I plug it into my formula, even though we know the plane's speed is 2,200 over 3 feet per second, because it's traveling from right to left, we need to make that a negative so this all works out. In other words, we're moving in the negative direction along the x-axis. This distance is moving in a negative direction. Once we have that, we can solve. We end up with secant squared of 1.085 multiplied times d theta divided by dt is equal to a single number, and the number I got was like 0.26, I et cetera, et cetera. It's not a real nice fraction to deal with. So I ended up, I'm just going to call it right now 0.263047138. And then I'm going to divide it by secant squared. If you recall, secant is 1 over cosine. So you could also multiply this number times cosine squared of 1.085. And what I ended up with was that the change in theta with respect to time was about 0.05735. That would be in radians per second. So the actual gun has to increase by about 0.057 radians per second. That's the rate of increase on the angle of the gun. So once we've done that for 1 mile away, then we can do that for 0.2 miles away and directly overhead. Let's go through the same process for when the plane is 0.2 miles away. When the plane is 0.2 miles away, 5,280 multiplied by 0.2 is 1,056. So that means the plane is 1,056 miles away. I might as well figure out the angle theta. That becomes tangent inverse of 10,000 feet divided by 1,056 feet. And that's about 1.4656 radians. I'm going to round that. That's perfectly fine. The plane's speed is still the same. It's traveling at 500 miles per hour, which we saw was 2,200 over 3 feet per second. So I want to plug everything I can into, remember, this formula here. So we're not dealing with this formula anymore. We're dealing with this one. The theta is 1.4656. The distance we are away is 1,056. The rate of change is 2,200 over 3. But remember, I have to make that a negative because we're traveling left to right. Or excuse me, right to left, excuse me. And then I can solve. So I take these numbers, 10,000 divided by 1,056 squared, negative 10,000 divided by 1,056 squared. I multiply it times negative 2,200 over 3. And then I divide by secant squared of 1.4656, or if I'm clever, I can multiply times cosine of 1.4656 squared. And when I did all of that calculation, I ended up with d theta dt equaling 0.07 0.25056, blah, blah, blah. Again, this is radians per second. If you compare that to what we did with 1 mile away, notice that when the plane is closer, the angle has to change at a much faster rate. We went from 0.05 radians per second to 0.07. And that should make sense with your common sense understanding of how this works. As this plane gets closer and closer and closer, this gun is going to have to change at a much faster rate. It's going to have to change a lot quicker as the plane gets closer and closer and closer. I copied and pasted, and let's do the last one. It went immediately overhead. So when the plane is immediately overhead, we're at 0 feet. Now, if you try to type this into your calculator, you're probably going to get an error because we can't divide by 0. That doesn't necessarily mean that the angle doesn't exist. We just have to realize what that angle is. If the plane is immediately overhead up there, then what's happening is that this angle theta is actually a 90-degree angle, all right? Now, in terms of, again, we're using radians on my calculator, so 90 degrees is the same as pi over 2 in radians. So pi over 2 in radians, and again, we're at the 0 feet mark. So we can't find the radians with inverse tangent, but we can find it through common sense. And common sense tells us that the angle is pi over 2. So we go back to our formula here. We go pi over 2 times d theta dt, 10,000. This is a problem, isn't it? Divided by 0 squared times negative 2200 over 3. And that's not a very nice thing, is it? We might say we should give up here. However, if you think of cosine of pi over 2, that's also 0. So secant squared of pi over 2 is like 1 over 0 squared. So we kind of have a 1 over 0 squared on both sides. And if you wanted to get into limits and things of that nature, you could actually, you might be able to, if you multiplied both sides by cosine, you may just be able to take limits and reduce it and make some sense. I'm not going to do that because I am just going to say when you're immediately overhead, this technique does not work. All right. So we're dividing by 0 in too many places. And so this technique is not going to work when we have something, when the plane is flying immediately overhead. So it's okay to be 0.2 miles away. It's okay to be a mile away. But when we're immediately overhead, this technique is not working for us. And that's okay. It's okay to have, one of these not work for us. Just a reminder that I'm saying it doesn't work for us. We could go through some limit ideas and get an answer, but that's going to take a much longer time. So we're just going to cut this off and say, because we're dividing by 0, I don't want to use this technique. I would like you to try the following problem on your own. We're once again going to be dealing with triangles, moving triangles, and we have a ladder leaning on the side of a barn, and it's being pulled away from the barn at the base at a rate of 1 foot per second. And we want to figure out how the top of the ladder is moving down the barn. So this is not talking about angles anymore, but once again, distances. So it might be a little bit more straightforward for you. Push pause and try this problem.